Good morning, good afternoon, and good evening, and welcome to my talk, Machine Learning for Capacity Management. My name's Dave Page. I've been working at EDB for nearly 14 years now. I'm currently working in our CTO office, spending most of my time on research and development and working with some of our larger accounts. I've been working on PostgreSQL for over 20 years now. There I serve on the core team and act as the lead developer for PGAdmin, as well as working for various non-profit organizations and other teams within the project. So what is capacity management? According to Wikipedia, capacity management's primary goal is to ensure that information technology resources are right-sized to meet current and future business requirements in a cost-effective manner. In practice, what this means is having an understanding of when resources might need to be increased or decreased to support the software and the applications that we're running. For example, when am I going to run out of disk space on my database server? Or when might I have a spike in user load and that requires me to provision more resources, maybe scale up the database cluster to cope with it. Classic capacity management tools tend to focus on trends. When will I run out of disk space? How many rows will this table contain in 6 months' time? At the current growth rate, how many servers will I need to support my users in 3 years? Those are all things that generally tend to trend upwards or downwards. So whilst the middle one then, how many rows will be in this table in 6 months' time, might fluctuate depending on what your application's actually doing. Typically, you're usually using more disk space every day. Hopefully your business is successful, so your number of users every day is going to grow, so you need to provide additional capacity to support those. Many of these tools, including, for example, EDB's Postgres Enterprise Manager, tend to use things like linear trend analysis to do capacity management reports. So we'll collect a bunch of metrics over time. We'll monitor the amount of disk that's used every 5 minutes, 10 minutes, or whatever. And then we'll take that data and we'll extrapolate it out, either to a point in time, so where will I be in 3 months from now, or to a threshold value, so when will I hit 90% of my usage, or when will my database hit 1 terabyte in size. Once we've got that information, and you can see an example in the graph there, we can plan based on those results. So we know when we need to provide more disk space. We know when we're likely to need to have more capacity for more users. One of the limitations with capacity management, or traditional capacity management, is that requirements are generally more complex than simple upward or downward trends. A lot of the time we have seasonality, so user numbers may go up and down during the day. They may be higher in the daytime on weekdays than at night or the weekend. Or system load may be much higher on the last day of the month because we're doing month-end financial batch processing. We also can get noise in the metrics we collect. Typically we can say there's not always going to be 127 users on the system at 2 p.m. on a Tuesday. One day there might be 127, the next day it might be 129, the next Tuesday it might be 110. Noise can affect linear trend analysis in ways that we might not always see. So why do we care about that? Well, if we're using utility or cloud-based computing, which is very common these days, we can easily scale up or down in anticipation of load spikes. We can scale down when capacity is not required to save money. And we can minimize unnecessary fluctuations in scale. So if we have a better understanding of when we're likely to see load spikes, then we don't find ourselves scaling up again because we didn't realize that a spike was on its way. And the issue with noise is sometimes it can make it harder to see or understand trends. And we need to cut through that noise to really understand what's going on. So, this talk is primarily about machine learning. specifically deep learning, the way that we can apply a particular technique using neural networks to help us understand and better manage our capacity of our systems. We're going to be using Python throughout the talk, specifically the TensorFlow 2 library. The techniques that I'll talk about here can be used standalone, so you can just write Python scripts to run them, or you can quite easily use PL Python 3 if you want to analyze data that's already in Postgres. Maybe in your situation it makes sense to do that within the database server if that's where the data already is. So, what is TensorFlow? TensorFlow is a free and open source software library for machine learning. It can be used across a range of tasks but has a particular focus on training and inference of deep neural networks. Again, that's the Wikipedia definition. Essentially, TensorFlow is an open source machine learning library that was originally born as part of the Google Brain project and made open source. It's particularly easy to use and very easy to learn. And like many of the machine learning languages out there, it tends to focus primarily on Python as the platform of choice, but you can use it with other languages as well. There is support for Java and C++ and Go and so on. So how are we going to get TensorFlow installed? Pretty simple. If you've got Python 3.5 or later installed already, create a virtual environment, as you can see there, and simply run pip install TensorFlow. If you want to use this within PostgreSQL, then you must use the interpreter that's used by PL Python 3. So if you're running on a Linux system such as Debian or Red Hat, then that's typically the system's Python interpreter. In my case, I'm running this on my Mac, so I'm using the EDB language pack, which is there to provide the Python, Perl, and Tcl support for our PostgreSQL 13 packages. And we must make sure that we're using that particular Python interpreter when we install TensorFlow, so it then is available to the Postgres instance. Again, very simple, just run the right installation of pip and install TensorFlow. Now, I will note at this point that you may also want to install a couple of other libraries. NumPy is extremely useful. Matplotlib is useful if you want to plot graphs for monitoring the success, the learning rate, and various other things related to your neural networks. And Pandas is also a very useful library for dealing with data sets within Python. So let's look at what we're actually going to build here. We're going to create a deep neural network in the WaveNet architecture. Multiple one-dimensional convolutional layers will be added to the model. Now, a layer here is basically a set of neurons, each of which is essentially a filter with trainable parameters, weights and biases that will be adjusted as we learn the data. We're going to configure an increasing dilation rate to detect seasonal patterns. So lower layers will learn short-term patterns and higher layers will learn long-term patterns. As you can see from the diagram, the neurons on the lower layer will feed up into smaller numbers of neurons on the higher layers. The WaveNet architecture was originally designed for audio analysis, and if you think about audio, it's just a series of samples along a timeline, and that makes WaveNet pretty ideal for analyzing time series data such as we have here. We need to prepare our input data as well. It's usually a critical part of machine learning. If you're doing text-based prediction and similar textual analysis type tasks, you need to remove things like punctuation. You need to structure sentences such that the network can understand them and analyze them properly. If you're doing regression type analysis, you'll need to remove outliers, for example. Thankfully, with time series prediction, we don't actually require too much work on this front. Time series data really just consists of a timestamp, i.e. when was the metric recorded, and the value of the metric. So that it's pretty simple and straightforward. The main thing that we want to do is make sure that our metrics are recorded equidistantly over the time period. We don't want varying gaps between the different samples. We want those gaps to be as consistent as possible. We do need to prepare the data ready for the network. And what we're going to do is split it into training and validation sets. We're going to actually split it into 4 separate arrays: training timestamps and training metrics, validation timestamps and validation metrics. The network doesn't actually care about the timestamps. All it cares about is the fact that there's a sequence of data, the metrics. We're only actually going to use the timestamps when we plot the results on a graph so that we can visualize them. We're going to use the training data to train the network. That is, we'll take multiple passes of reading the training data and then adjusting the parameters within the network such that we get the result, the metric value that we expect. And we're going to validate that with the validation data. So based on each pass of training, as we adjusted our weights and biases in the network, the validation data is then going to be used to figure how effective that training was. And then we can continually adjust the weights and biases as needed to fine-tune the model. So here's some Python code. This is using the Keras API within Tensorflow to create the model. We first of all create a sequential model. So that's just a model that consists of multiple layers that are added one after the other. We start with creating an input layer. We tell it the input shape is none, 1. So that basically means we're going to give it one input value at a time. And then for each of our different dilation rates, we add a new convolutional layer. Finally, we add a single layer, which is our output layer. So one neuron to give us one value out per time step. You will have noticed there are various parameters in the layers that we added. I'm going to list those out separately from the code just to give you an idea of what they all mean. So filters is the number of neurons in the layer. That corresponds directly to the required output dimension of that layer. So the number of values we want to get out from the layer. The kernel size is the length of what's known as the one-dimensional convolutional window. Whenever we compute a value, we don't just look at one input value. We're going to look at multiple of them. So it's a window, if you like, saying the number of time steps that we're going to use to compute each following output value. Strides is the number of time steps that the filter moves as it processes the input. So if you think about it in terms of that window, the kernel size, how far across the data set that moves in terms of time steps as we process the input values. Padding is a slightly complex one. Essentially, we need to pad the values and create some additional values, because if you think about a kernel size where we're looking at 3 time values at once, when we get to either the beginning or the end of the data, we need a couple of extra values to make up those 3. Otherwise, we can't analyze the first 2 or the last 2 values in the time series. We use causal padding here. What that does is add values to the beginning of the time series. We don't want them on the end of the time series, because then we end up predicting future values based on padding that was already added to the future. Finally, the activation function helps the network handle nonlinear and interaction effects. So this is where different variables in the network can be affected by one another. ReLU is a simple algorithm that works here in many cases. I don't have time in this talk, unfortunately, to go into exactly what this is doing, so we'll leave that up as an exercise for anyone that wants to explore it further. So having created the model, this is what it actually looks like. So as you can see, we've got a input layer with 32 neurons at the beginning. And then we've got multiple what are known as hidden layers, again with 32 neurons. And then the final output layer with 1 neuron in it to give us the one value that we want out, so 1 value per time step. That results in 10,529 trainable parameters, that is the weights and the biases on each of those neurons within the network. Training. So now that we've created a network, we need to train it. We're going to use supervised learning here. So that is, we're going to train the network based on data and results that we already have, i.e. the set of metrics that we already have. We run through multiple iterations, as I mentioned earlier. These are sometimes known as epochs. That's going to be done using our training data set. With each epoch, the weights and the biases of the neurons are adjusted to tune the network. And we then use the validation data set to assess the accuracy of the model. We use a loss function to measure that accuracy. In this case, it uses the Huber algorithm. Let's take a look at the code behind the model. So first of all, we create an optimizer. The optimizer object is used to figure out how best and with what values to adjust the weights and biases with each pass through the training process. We then compile the model that we've created. We pass it the loss algorithm that we want to use. We use the optimizer that we've defined, and we tell it that we want to monitor the mean absolute error metric. We then create a couple of checkpoints. I'll go into these in more detail in the next couple of slides. And then finally at the bottom on line 134, we can see that we run the model.fit member function. And what that does is initiates the training process. So we pass it the training data set, we tell it to run for the number of epochs that we require, we pass it the validation data set, and we tell it the callbacks to use. So early stopping, you'll have noticed that one of the callbacks specified was called early stopping. This is to prevent something that's called overfitting, which occurs when the network learns the data rather than the patterns. Essentially, this happens if we run through too many training epochs. And we need to stop the training process before that happens. Otherwise, what's likely to happen is the network will work very well with the training data, but it will work terribly with any other data. Essentially, what we do with this callback is simply say, if we haven't made any significant progress over the last 50 epochs, then stop training. And then that hopefully will prevent us from overfitting. The second callback we were using was a checkpoint callback. So one of the things that you can see on the graph on the right hand side here, this is the training and validation root mean square error versus the training epoch for a regression network. And you can see the error rate doesn't drop consistently. It goes up and down at various points. So what we do is with every epoch, we assess the accuracy of the model. And if we've made an improvement over all previous epochs, then we save the model. We take a checkpoint. And then once training is actually complete, we load the last saved model because we know that's the best one that we've got. There are various things that we can do to tune the model further. We can experiment with various parameters. And frankly, experience helps here. This is not something that you're just going to be able to get right immediately. You're going to need to play with it, learn, understand what's going on. We can increase the number of epochs. You can plot a graph like the one you saw on the previous slide, and see actually is our learning not improving, or is it continuing to improve past the point at which we stop. You might adjust the learning rate, which effectively can adjust how much the weights and biases are tweaked on every epoch. You could try a different optimizer. My experience is that Adam is usually the best, and I've seen various blog posts where people have compared them and come to a similar conclusion. But it might be worth trying something else for your particular situation. Experiment with the number of layers and filters in the model. Try a different activation function other than ReLU. Adjust the kernel size and stride, or try different ratios of training to validation data. Again, this is all about experimentation and trying out things to see what improves the results that you get with your data. So testing, now that we've trained our model, we want to see how well it did. How did the validation show that we're correctly predicting results using our model? I did the testing with the code I wrote in two different ways. First of all, one of the tutorials I used had some generated data, some code written in Python that generated data to play with. So I worked with that quite a lot. I also set up a Postgres system running Postgres Enterprise Manager and a workload generator. So I could actually monitor that system as a real example of Postgres workload. So looking at the generated data first of all, as I mentioned, this was generated in Python. It includes three main components. So seasonality. So these are the up and down spikes that you see. And then the horizontal flat level layers, sections in between. It includes trend. So you'll notice that the values are generally trending upwards from left to right. And it includes noise, the variations that you see, the zigzags, the very fine zigzags. And this is fairly typical of the sort of data that we're talking about in practice. You remember the classic linear trend analysis type capacity management tools will typically only detect that upward trend. So here are the results I saw from training a model and then using it to predict with that data. So the blue part of the data is what was used for training the model. And the orange part of the data was also generated, and that was the validation set. Having trained the model with the blue samples and then validated using the orange samples, we could then actually forecast the data that overlays the validation data. Now, obviously, we could forecast out further than this, but the point of what I'm trying to do here is indicate how well the model actually performed. And as you can see, the green forecast data pretty well mirrors the validation data, i.e. what actually occurred. We've got the upward trend, we've got the seasonality, and we've got a small amount of noise, but for the most part, the noise is ignored. Having proven that this works, we can then take that further and use it to predict actual unknown data. I also simulated workload, as I mentioned. So these are all metrics recorded from PostgreSQL. I spent some time actually writing a workload generator, which you can find on the EDB GitHub account. That was designed to run the same workload that is run by the pgbench utility that comes with Postgres, but to vary the number of users over time. You can define a profile that says over a period of a week, these are the different numbers of users at any particular time of the day. What I recorded was simply the number of rows in pgstat activity. I had a cron job that ran every 5 minutes and appended to a CSV file with a timestamp and a metric. And the aim here was really to have what admittedly is a fairly simple metric, but easily could have been disk usage or CPU usage or any other metric. But one that was simulating the real life up and down workload that you would see on a system over a period of time. I mean, for example, you can see at a couple of points there are lower peaks of numbers of users. So that would be at the weekend when there are fewer users on the system on a Saturday and Sunday. And here's the results from that. Again, the training data is shown in blue. The orange line is the validation data, so that's what was actually recorded. But then the green line is forecast from the training that was done using the blue data. And again, we can see that it pretty closely mirrors exactly what we see in the validation data. So we've predicted with a fairly high degree of accuracy here. The only thing, again, that's missing or is smoothed out is the noise, which is fine, because having the noise be smoothed out can actually make it much easier for us to read and understand what's going on. So obviously we can see how this can be used for capacity management. You can understand that we can use it to see when we're going to run out of disk space, which we could do with traditional linear trend analysis. But you can also see how that we can monitor the system and understand load at different times of the day or different seasonalities. So peaks that might happen monthly, increased numbers of users around the holiday period, for example. And we can use that information to do much more complex capacity management. Scaling up and down the resources in the cloud, for example, so that we save money when we have fewer users and we have the capacity we need when there are more users. But we can also use this for regular monitoring and alerting. If you think about classic alerting, systems might be configured to tell you when the number of active users exceeds 200. Well, that's great at peak times, but actually there might be something odd going on if at midnight on a Sunday there are 200 users, and you'll never know about it. On midnight on a Sunday, it might be normal just to have a couple of users. And although the system could handle the load, there might actually be some other problem that has resulted in there being multiple users at that period of time. For example, somebody might be attempting to attack the system, and you want to know about that. This technology allows us to be able to dynamically configure thresholds based on predicted usage patterns. So instead of just having a very static, tell me when there's more than 200 users, we can tell me when there's 10 users more than I would normally expect at this time of the week, in this month, and so on. And that can allow us to do much more effective monitoring and alerting than we might be able to do just with traditional mechanisms. So what are our conclusions? Machine learning techniques, we can more accurately predict metrics with seasonality and trend. We can scale up and scale down to deal with demand and save money. It can help us plan for additional resource requirements above and beyond what we could do with traditional linear trend analysis. We can also detect abnormal conditions, taking into account the day, week, month, etc. So that concludes my talk for today. Thank you very much for taking the time to listen. Some useful links on the screen right now. The workload generator that I mentioned, which you may find useful for your own testing. The code I've been writing while I've been working on this and other related machine learning technologies you can find on my GitHub account. You can also find various blogs and things that I've written on the links below. Thank you very much. Have a great day.